Welcome to Space Sleep. Tonight, we will travel through galactic cemeteries, far beyond the glowing spiral arms that fill astronomy books, far beyond the bright galaxies captured by telescopes. Tonight, we will drift into the graveyards of the universe, into places where light is fading, where stars no longer awaken, where entire galaxies slowly become cosmic ghosts. As you settle in, while you're getting comfortable, take a brief moment to like and subscribe, only if you are truly enjoying this journey. And tell us in the comments the location and time where you are listening right now, so we can all drift through the universe together. Now, imagine distances so immense that light requires millions of years to cross them. Imagine structures so large that they contain hundreds of billions of stars. Imagine islands of light floating alone within oceans of infinite blackness. These islands are galaxies. Some are young, some are mature, some are bursting with life, and some are dying, or perhaps already dead. Tonight we begin our journey among these cosmic ghosts, the dead galaxies, the silent cities of the universe, the abandoned kingdoms of the stars. And our first question is simple. What exactly is a dead galaxy? Chapter 1. What is a dead galaxy? The phrase sounds dramatic. A dead galaxy. It sounds like something from science fiction, a place where ancient civilizations disappeared, a region haunted by forgotten stars, a celestial ruin drifting through the darkness. But the truth is both less dramatic and somehow even more mysterious. Because when astronomers speak about a dead galaxy, they are not usually talking about destruction. The galaxy still exists. The stars are still there. The gravity remains. The structure survives. Nothing exploded. Nothing vanished. Yet something important has ended. Something fundamental. Something that once filled the galaxy with light. The birth of stars. To understand what makes a galaxy dead, we first need to understand what makes a galaxy alive. And to understand that, we must travel backward through billions of years, back to the beginning. The universe was not always filled with galaxies. There was a time when no galaxy existed, no stars, no planets, no black holes, only an expanding sea of energy and particles. After the event we call the Big Bang, the universe slowly cooled. Tiny differences in density emerged. Regions with slightly more matter began attracting more matter through gravity over millions of years. Those regions grew and grew and grew like invisible seeds planted throughout the cosmos. Eventually, enormous clouds of hydrogen gas formed. Gravity squeezed the gas together. The pressure increased. Temperatures rose. And for the first time, stars were born. The first stars transformed darkness into light. They illuminated a universe that had once been completely black. Around them, more stars formed, then clusters, then vast collections, then galaxies. Every galaxy began as a place of creation, a factory producing stars, a cosmic nursery, a gigantic ecosystem powered by gravity. And this process continues today. Even now, some galaxies are actively creating new stars. Deep within their clouds of gas and dust, new suns ignite every year. Some galaxies create a few stars annually. Others create hundreds. Some create thousands. The universe remains alive with stellar birth. Astronomers often call these galaxies star-forming galaxies, living galaxies, active galaxies, galaxies with ongoing creation. If we could somehow observe one up close, we would see enormous clouds glowing softly, dense regions collapsing inward, young stars emerging from cocoons of gas, brilliant blue stars shining intensely, nebulas stretching across thousands of light years. Constant change, constant renewal, constant life. But eventually, something begins to change. Not suddenly, not violently, slowly. over hundreds of millions of years, then billions. The raw material starts to disappear. The gas becomes depleted. The stellar nurseries begin closing. Fewer stars are born, then fewer still, then almost none. The galaxy enters old age, and eventually, the births stop. This is the crucial point. A dead galaxy is not a galaxy without stars. It is a galaxy without new stars. That distinction changes everything. Because when most people imagine a dead galaxy, they imagine darkness, an empty void, a celestial corpse. But many dead galaxies remain incredibly bright. In fact, some contain hundreds of billions of stars. The difference is that those stars are old, very old. The galaxy is no longer producing replacements. Imagine a city, a vast city filled with people. Buildings stand tall, roads remain intact, lights still glow in the windows. From a distance, everything appears normal. But imagine that no children have been born there for generations. The population slowly ages. No new life arrives. No future generations emerge. The city still exists, but something essential has stopped. In a sense, it has become a ghost of its former self. This is remarkably similar to what happens inside a dead galaxy. The stars remain, but the cycle of renewal has ended. Astronomers sometimes refer to this process as quenching, an unusual word. Quenching, like extinguishing a fire, because star formation behaves in many ways like a flame. As long as fresh fuel exists, the fire continues. But when the fuel disappears, the fire gradually dies. Galaxies experience the same fate. Without cold gas, new stars cannot form. Without new stars, the galaxy slowly ages. Without renewal, the galaxy becomes dormant, quiescent, silent, dead. Yet this raises another question. Why would a galaxy stop forming stars? After all, many galaxies contain extraordinary amounts of matter. Entire galaxies can possess enough material to create billions more stars. So what causes the process to end? The answer remains one of the great mysteries of modern astronomy. And researchers have discovered that there may not be just one cause. There may be many. Some galaxies appear to die because they simply use up their available gas. Over billions of years, generation after generation of stars consumes the raw material needed for future star formation. Eventually little remains. The stellar factories shut down. The galaxy grows old. Other galaxies suffer a different fate. They are stripped. As galaxies travel through crowded regions of space, they sometimes pass through enormous reservoirs of extremely hot gas. These environments can literally remove star-forming material from a galaxy. Like a powerful wind stripping leaves from a tree, the galaxy loses its fuel, and star formation ceases. Some galaxies appear to be killed by collisions. Ironically, galactic collisions can sometimes trigger star formation, but in other cases, they can also disrupt the delicate conditions necessary for future stellar births. The result may be a brief period of intense activity, followed by permanent silence. And then there are the giants, the supermassive black holes. Nearly every large galaxy contains one, hidden at its center, invisible, yet enormously powerful. Some of these black holes become active. As matter falls inward, tremendous amounts of energy are released. The energy can blast through the galaxy, heating gas, disrupting clouds, preventing new stars from forming. In some cases, the galaxy's own central black hole may help shut down the very process that created much of the galaxy's light. A strange cosmic paradox, the heart of the galaxy contributing to its slow death. And yet, even after all this, a dead galaxy is not truly dead in the way we usually think of death. Stars continue shining, planets continue orbiting, gravity continues shaping the structure, time continues passing. The galaxy still moves through space, still interacts with neighbors, still exists for billions upon billions of years. This is why many astronomers sometimes prefer other terms: passive galaxy, quiescent galaxy, red galaxy, because these galaxies are not gone. They are simply no longer creating, no longer renewing, no longer giving birth to stars. And if we could stand inside one, the view might be surprisingly beautiful. Young stars burn blue, hot, bright, energetic, but old stars glow differently. They radiate softer colors, golden colors, amber colors, deep reddish light. A dead galaxy often appears warmer in color than a living galaxy, not because it is hotter, but because its population consists largely of aging stars. The galaxy becomes a vast sea of ancient sunlight, a place illuminated by stellar elders, a cosmic retirement home stretching across hundreds of thousands of light years. And the longer astronomers studied these galaxies, the more mysterious they became, because they discovered something unexpected. Dead galaxies are everywhere. Some are relatively nearby. Others existed when the universe itself was young. In fact, astronomers have found galaxies that appear to have died astonishingly early in cosmic history. Galaxies that somehow formed stars at incredible rates, grew rapidly, and then fell silent while the universe was still young. How could an entire galaxy age so quickly? Why did some galaxies die early while others continue producing stars billions of years later? What invisible forces determine the lifespan of a galaxy? And perhaps the most haunting question of all, what does the future hold for our own galaxy? Because the magnificent spiral we call home, the Milky Way, is still alive. Stars are still forming. Nebulas still glow. New suns continue appearing within its spiral arms. But nothing lasts forever. Not stars, not galaxies, not even the grand structures that dominate the universe. One day, billions of years from now, the Milky Way itself may begin the long transformation from living galaxy to cosmic ghost. And as we drift deeper into the darkness of the universe, we will discover that some galaxies have already completed that journey. Ancient structures wandering through space, filled with old stars, devoid of creation, silent witnesses to the passage of cosmic time, ghosts among the galaxies. And the deeper astronomers looked into the universe, the more of these ghosts they found, waiting in the darkness. Continuing directly from the last sentence, Chapter 2, the first signs of death. Death rarely arrives suddenly, not for stars, not for galaxies, and not for most things in the universe. Instead, it often begins with small changes, subtle changes, changes so gradual that they can pass unnoticed for millions of years. Imagine an ancient forest. At first, it appears healthy. The trees still stand, the leaves still move with the wind, birds still sing among the branches. But deep within the forest, something has begun to change. Fewer young trees are appearing. The oldest trees continue standing. Yet the next generation grows smaller, then smaller still. The forest remains beautiful, but its future is already shifting. A galaxy experiences something remarkably similar. The first signs of galactic death do not appear as destruction. No giant explosion tears the galaxy apart. No catastrophic event suddenly extinguishes billions of stars. The galaxy remains magnificent. At first glance, nothing seems wrong. Its spiral arms still sweep gracefully through space. Its stars still shine. Its planets still orbit. Its gravity still binds everything together. Yet beneath the beauty, the future has already begun to change. Because the most important activity inside a living galaxy is not the light produced by existing stars. It is the birth of new ones. Star formation is the heartbeat of a galaxy. As long as new stars continue appearing, the galaxy remains alive, renewing itself, replenishing itself, preparing future generations. But eventually, that heartbeat begins to slow, not dramatically, Not all at once. One stellar nursery becomes quieter, then another, then another. The great factories of creation begin producing fewer stars. At first, the change is almost impossible to notice. A galaxy that once created 10 new stars each year might create 9, then 8, then 7. Millions of years pass, then hundreds of millions. The decline continues, like a slow-moving clock, like sand slipping through invisible fingers. And throughout this process, most of the galaxy remains unchanged. The older stars continue shining exactly as before. An observer living on a planet within the galaxy might never notice anything unusual. The night sky would still be full of stars. The galaxy would still appear alive, but astronomers looking from afar and measuring carefully would see the difference. They would notice that fewer young stars are appearing, and young stars are special, very special. Young stars are the brightest stars in a galaxy. Many are massive, extremely hot, extremely luminous. Their light shines with brilliant blue and white colors. When astronomers see large populations of blue stars, they know that star formation has occurred recently. Because massive blue stars do not live long. Some survive only a few million years, a blink of an eye in cosmic history. If blue stars exist, new stars must still be forming. A galaxy filled with blue stars is like a city filled with children. Evidence of youth, evidence of renewal, evidence of life. But as star formation declines, fewer blue stars appear. The existing ones eventually die, and no replacements arrive. Gradually, the galaxy begins changing its appearance. The transformation is almost imperceptible, yet it is profound. The bright young stars fade from the population. The older stars become increasingly dominant. The galaxy is growing older, not because its stars are aging individually, but because its entire stellar population is aging together. Like a civilization slowly losing its youngest generations, the average age rises, the energy changes, the character changes, the future changes. But what exactly causes star formation to slow? To answer that question, we must visit the stellar nurseries themselves. Throughout living galaxies, enormous clouds of gas drift through space. Some span dozens of light years. Others stretch across hundreds. These clouds are primarily hydrogen, cold, dense, dark. At first glance, they may appear empty, yet they are among the most important structures in the universe. Because stars are born inside them, gravity slowly pulls gas together. The cloud becomes denser, the pressure increases, the temperature rises. Eventually, a new star ignites. A new sun begins shining. A new chapter begins. For billions of years, this process repeats, again and again, generation after generation. The stellar nurseries never seem to rest, but eventually, the nurseries begin disappearing. Some are consumed, their gas transformed into stars. Others are dispersed by stellar winds. Others are heated by energetic processes. Some are stripped away entirely. Regardless of the cause, the result is the same: less cold gas, fewer nurseries, fewer births. The galaxy begins losing its ability to create. And this may be the most important distinction between a living galaxy and a dying one. The stars themselves are not the true source of life. The gases, the stellar nurseries are. The future resides not in the stars already shining, but in the clouds capable of creating new ones. When those clouds vanish, the future begins vanishing with them. Imagine walking through a city. The buildings remain, the roads remain, the lights remain, but every school has closed. Every hospital maternity ward is empty. Every playground is abandoned. The city still exists, yet something fundamental has changed. Its future population has already begun disappearing. A galaxy entering old age experiences a similar transformation. Its future stars are no longer arriving, and astronomers can actually witness this process. Modern telescopes do far more than simply photograph galaxies. They analyze their light, every wavelength, every color, every subtle signature hidden within the glow. Light carries information, information about temperature, composition, motion, age, history. By studying galactic light, astronomers can reconstruct the life story of entire galaxies. Even galaxies located billions of light years away. They can estimate how rapidly stars are forming, how much gas remains, how old the stellar population has become, whether the galaxy is thriving or declining, or already dead. It is one of the greatest achievements of modern astronomy to look across billions of light years and diagnose the health of an entire galaxy. And what astronomers discovered was fascinating. Galactic death is often not a single event. It is a transition, a long transition. A galaxy may spend hundreds of millions of years, or even billions, in an intermediate state, not fully alive, not fully dead, existing somewhere in between. Astronomers sometimes describe this region as the Green Valley, a fascinating stage of galactic evolution. On one side are active galaxies, blue, bright, producing stars. On the other side are passive galaxies, red, quiet, aging. The Green Valley lies between them, a kind of cosmic middle age, a period of transformation, a period of uncertainty, a period when the future direction of the galaxy is being determined. Some galaxies cross this valley quickly, others linger there for extraordinary lengths of time, slowly drifting toward old age, slowly surrendering their youth, slowly becoming relics. And nowhere is this transformation more striking than in spiral galaxies. Spiral galaxies are among the most beautiful structures in existence. Their sweeping arms resemble gigantic celestial whirlpools. Within those arms, star formation flourishes. Bright clusters illuminate the darkness. Nebulas glow. Young stars radiate blue light. The galaxy feels alive, dynamic, energetic, hopeful. The Milky Way is such a galaxy. Even now, new stars continue appearing within its spiral arms. The galaxy remains vibrant, but imagine billions of years passing. The gas reservoirs shrinking, the stellar nurseries disappearing, the blue stars fading, the spiral arms becoming less distinct. The galaxy would still exist, yet its appearance would slowly change. Its personality would change. Its story would change. The vibrant spiral would gradually become something quieter, something older, something more contemplative, a relic, an archive of ancient light, a museum filled with stars born long ago. This transformation is not tragic, at least not by the standards of the universe. It is simply part of the cycle. A galaxy cannot remain young forever, just as stars cannot remain young forever, just as civilizations cannot remain young forever. Everything ages. Everything evolves. Everything changes. The universe itself is a story of transformation, and galaxies are among its most beautiful examples. They begin as chaotic collections of gas. They grow. They flourish. They create generations of stars. They shape planets. They illuminate the darkness. And then, slowly, almost imperceptibly, they begin to age. The stellar nurseries become quiet. The blue stars become rare. The future becomes smaller than the past. And somewhere within the immense silence of intergalactic space, a living galaxy takes its first steps toward becoming a cosmic ghost. Yet a mystery remains. What ultimately causes this process? Why do some galaxies lose their stellar nurseries, while others continue creating stars for billions of years longer? What force extinguishes the fires of creation? What mechanism turns a thriving galactic ecosystem into a silent relic of ancient light? To answer that question, we must investigate one of the most powerful and surprising suspects in the universe, a force hidden at the center of nearly every large galaxy, a force capable of influencing entire star systems, entire stellar populations, perhaps even the fate of galaxies themselves. The supermassive black holes. I'll continue directly into Chapter 4 and leave the ending open for the next chapter. Chapter 3. The giants that ate too much. At the center of nearly every large galaxy, there is a monster, invisible, silent, almost impossible to imagine. A monster so strange that for decades many scientists doubted such objects could even exist. And yet, today we know they are everywhere, hidden within the hearts of galaxies, including our own. These are the supermassive black holes, among the most powerful objects in the universe, and perhaps among the most important, because some astronomers believe that the fate of entire galaxies may depend upon them. To understand how a galaxy dies, we must first understand these cosmic giants. And to understand them, we must begin with a simple question. What is a black hole? Most people imagine a giant vacuum cleaner, a cosmic monster roaming through space, devouring everything nearby. But reality is more subtle and far more fascinating. A black hole is a region where gravity has become so powerful that nothing can escape, not planets, not stars, not gas, not even light itself. The boundary surrounding a black hole is called the event horizon. Cross that boundary, and there is no return, no signal, no message, no escape, only a one-way journey inward. Black holes come in different sizes. Some form when massive stars die. These stellar black holes may contain several times the mass of our Sun. Others are larger, much larger. And then there are the giants, the supermassive black holes. These monsters can contain millions, billions, or even tens of billions of solar masses. Imagine compressing the mass of billions of stars into a single object, an object hidden deep within a galactic core, an invisible king sitting upon a gravitational throne. At the center of the Milky Way lies one such object, a supermassive black hole known as Sagittarius A star. Its mass is roughly 4 million times that of our Sun. 4 million suns, compressed into a region smaller than our solar system. And astonishingly, Sagittarius A star is relatively modest. Elsewhere in the universe, even greater giants exist. Some contain billions of solar masses. Some are so massive that if our solar system were placed beside them, the comparison would feel almost absurd. Yet for much of their lives, these black holes are surprisingly quiet. They sit silently within their galaxies, invisible, patient, almost dormant. And when dormant, they have little impact on the galaxy around them. Stars continue forming, gas continues drifting through space. Life goes on, but sometimes something changes. Sometimes a black hole begins feeding, and that is when the real story begins. Contrary to popular belief, black holes do not actually suck things in like vacuum cleaners. Matter must still fall toward them. Gas clouds must drift inward. Stars must wander too close. Material must find its way toward the center. But when it does, the consequences can be extraordinary. As gas approaches a black hole, it rarely falls directly inward. Instead, it begins orbiting, spiraling, whirling faster and faster. The gas forms a structure known as an accretion disk, a gigantic rotating disk of superheated matter. Friction builds, temperatures rise, the gas becomes unimaginably hot, millions of degrees, sometimes tens of millions. The result is one of the brightest phenomena in the universe, a remarkable paradox. The black hole itself remains perfectly dark, yet the material falling into it becomes incredibly luminous. In some cases, the center of a galaxy can outshine all the stars surrounding it. Hundreds of billions of stars, overpowered by a single feeding black hole. Astronomers call these active galactic nuclei, or AGNs, active galactic nuclei. The name sounds technical, almost harmless, but these objects are anything but harmless. They are among the most energetic engines in existence. They release enormous quantities of radiation, powerful streams of particles, immense amounts of energy, all generated by matter falling toward destruction. Some active galactic nuclei become so bright that they can be observed across billions of light years, across much of the observable universe. These extraordinary objects are known as quasars. Quasars, the cosmic lighthouses, the beacons of the early universe. For a period during the 20th century, astronomers were baffled by them. Telescopes revealed strange points of light, objects that looked like stars. Yet something seemed wrong. They were too bright, far too bright. The energy they produced exceeded anything scientists expected. Eventually the truth emerged. They were not stars at all. They were galaxies, distant galaxies, galaxies whose central black holes had become ravenous, galaxies illuminated by feeding monsters. A single quasar can emit more energy than entire galaxies. Imagine the light of hundreds of billions of stars, combined and concentrated, produced by a region smaller than the galaxy itself. The numbers become difficult to comprehend. Some quasars release more energy every second than our sun will produce throughout its entire lifetime. Every second. The universe occasionally creates objects so extreme that human intuition simply breaks down. Quasars are among them, and during the early universe, they were far more common. Young galaxies contained enormous supplies of gas. Black holes fed aggressively. The cosmos was alive with brilliant quasars, ancient monsters consuming cosmic fuel. But astronomers eventually discovered something surprising, perhaps even disturbing. These feeding black holes were not merely passive observers of galactic evolution. They were influencing it, shaping it, controlling it, perhaps even ending it. This realization transformed our understanding of galaxy death. For many years, scientists assumed galaxies and black holes evolved independently. The galaxy formed stars. The black hole sat at the center. Two separate stories, two separate systems. But observations told a different story. Galaxies containing larger central black holes often exhibited particular characteristics. Patterns emerged. Relationships appeared. Connections became impossible to ignore. It was as though the black hole somehow knew what was happening throughout the galaxy. And somehow, the galaxy knew about the black hole, despite the enormous distances involved. Then came one of the most important ideas in modern astronomy: AGN feedback. Feedback. A simple word, yet it may explain why entire galaxies stop creating stars. When a supermassive black hole becomes active, it releases energy into the surrounding galaxy, a tremendous amount of energy. This energy does not remain confined to the galactic center. It spreads outward, sometimes through radiation, sometimes through powerful winds, sometimes through colossal jets. These jets are among the most spectacular structures in the universe. Narrow beams of particles, traveling at speeds approaching that of light, extending thousands, sometimes millions, of light years into space. Imagine a beam so large that it dwarfs entire galaxies. A structure capable of influencing regions larger than most civilizations could ever imagine. The black hole becomes a cosmic engine, and the galaxy feels its effects. One possibility is heating. Star formation requires cold gas. Cold gas can collapse under gravity. Cold gas can form stellar nurseries. Cold gas can create new stars. But when a black hole injects enormous amounts of energy into its surroundings, the gas heats up. Hot gas behaves differently. Hot gas resists collapse. Hot gas struggles to form stars. The raw material remains present, yet it becomes unusable. The fuel still exists, but the engine can no longer burn it. In this scenario, the black hole does not remove the gas. It simply prevents the galaxy from using it. The stellar factories begin shutting down, not because fuel vanished, but because the fuel became inaccessible. Another possibility is even more dramatic. Sometimes powerful winds generated by active black holes can physically expel gas from a galaxy. Imagine a hurricane. Now imagine a hurricane spanning thousands of light years, a storm driven by a feeding black hole. The outflow can push enormous quantities of matter outward, gas that might have formed future stars, gas that represented the galaxy's future generations. Blown away, lost to intergalactic space, the stellar nurseries disappear, the future disappears with them, and slowly, star formation declines. The galaxy begins aging, the galaxy begins dying. A remarkable irony emerges. The same black hole that grew inside the galaxy may ultimately help shut down the galaxy's future, a creation becoming a destroyer, a child influencing its parent, a monster fed by the galaxy, eventually contributing to the galaxy's decline. And perhaps the strangest part of all, the black hole itself remains tiny compared to the galaxy. A galaxy may span 100,000 light years. The region immediately surrounding the black hole is minuscule by comparison. Yet somehow, events occurring in that tiny central region influence the fate of hundreds of billions of stars. It is one of the most astonishing examples of interconnectedness in the universe. Small causes, enormous consequences, tiny regions, galactic scale effects. Astronomers now believe AGN feedback may be one of the primary mechanisms responsible for creating dead galaxies. Not the only mechanism, but certainly one of the most important. Without it, computer simulations struggle to reproduce the universe we observe. Too many galaxies remain active. Too many stars continue forming. The universe becomes unrealistically alive. To create realistic populations of aging galaxies, something must suppress star formation. Something must extinguish the stellar nurseries, and supermassive black holes appear capable of doing exactly that. Yet, many mysteries remain. Not every dead galaxy shows evidence of AGN activity. Not every active black hole kills star formation. Some galaxies recover, some do not. The details remain uncertain. The investigation continues. The universe rarely offers simple answers, but one conclusion seems increasingly clear. The giant hidden at the center of a galaxy is not merely a spectator. It is a participant, a powerful participant, perhaps one of the most influential actors in the entire story of galactic life and death. And as astronomers looked beyond individual galaxies, they discovered that black holes were not the only killers. Entire environments could contribute to galactic death. Regions where thousands of galaxies live together. Regions so crowded, so massive, and so hostile that even healthy galaxies could begin to wither. To understand those cosmic graveyards, we must leave individual galaxies behind and venture into the vast kingdoms known as galaxy clusters. Chapter 4: Galactic Cannibalism. When most people imagine space, they imagine emptiness, vast emptiness, infinite emptiness, an ocean of darkness where objects remain forever separated. And in many ways, that picture is correct. The universe is astonishingly empty. The distances between stars are immense. The distances between galaxies are even greater. A beam of light requires more than 4 years to travel from our sun to the nearest star. To cross the Milky Way, that same beam requires roughly 100,000 years. To travel between large galaxies, millions of years may be needed. Everything seems isolated. Everything seems alone. And yet, despite these enormous distances, galaxies collide. Not occasionally, not rarely, but constantly. Across the history of the universe, countless galaxies have crashed into one another, merged together, consumed each other, destroyed each other's structures. and emerge transformed. The universe is not merely a place of creation, it is also a place of cosmic cannibalism. Entire galaxies feeding upon other galaxies. Entire stellar civilizations of stars swallowed into larger systems. And surprisingly, this process may play a major role in creating dead galaxies. To understand how, we must first understand what a galactic collision really looks like. The phrase itself can be misleading. Collision, it sounds violent, explosive, like two cars crashing together, like worlds shattering, like catastrophe. But galaxies are mostly empty space. The average distance between stars is enormous. When two galaxies pass through each other, most stars never collide at all. Imagine two clouds made of billions of tiny insects passing through one another in the sky. Some interactions occur, but direct impacts remain extremely rare. Galactic collisions are not primarily collisions between stars. They are collisions between gravitational systems, between structures, between destinies. The stars survive, the galaxies do not, and that distinction changes everything. Imagine looking at the night sky from a planet inside a galaxy undergoing a merger. For millions of years, nothing unusual would seem to happen. Then slowly, another galaxy would begin growing larger in the sky. At first, a faint smudge, a distant glow, a strange shape among familiar stars. As millions of years passed, the glow would become brighter, larger, more detailed. Eventually, its spiral arms might stretch across huge portions of the heavens. The sky itself would appear transformed, an entire galaxy hanging overhead, a second Milky Way dominating the darkness. And then, gravity would begin its work. Not suddenly, but relentlessly. The galaxies would pull upon one another. Stars would shift. Gas clouds would move. Spiral arms would stretch outward. The beautiful symmetry of each galaxy would begin to unravel. Long tidal tails would emerge. Great rivers of stars extending hundreds of thousands of light years into space. Some stars would be thrown outward. Others would fall inward. The orderly structure built over billions of years would begin coming apart. The galaxies would not die immediately, but they would never be the same again. As the interaction intensified, something unexpected would happen. Star formation would explode, at least temporarily. Enormous clouds of gas would collide, compress, collapse. New stars would ignite at extraordinary rates. The galaxy would experience a starburst, a frenzy of creation, a final celebration of youth. Regions that once produced a handful of stars each year might suddenly create hundreds or thousands. Massive blue stars would appear everywhere. Supernova explosions would become common. The galaxy would shine brilliantly. To an outside observer, it might appear healthier than ever, more active than ever, more alive than ever. But appearances can be deceptive, because this period of extraordinary activity often carries the seeds of future death. The starburst consumes fuel. Rapidly, aggressively, the galaxy burns through vast reserves of gas, material that might have supported star formation for billions of years, consumed in a comparatively brief cosmic moment, like a fire burning hotter and hotter until little fuel remains. And as the merger continues, other processes begin. The colliding galaxies channel enormous quantities of gas toward their centers. The central black holes awaken, feeding accelerates, active galactic nuclei ignite, quasars may emerge, powerful winds develop, radiation floods outward. Everything begins working against future star formation. The galaxy is simultaneously creating stars and preparing to stop creating them. A strange contradiction, a final burst of life before old age arrives. Eventually, the galaxies pass through each other. Then gravity pulls them back together. Again, and again, and again. Each encounter removes more energy from the system. Each encounter brings them closer, until finally, after hundreds of millions of years, the merger is complete. Two galaxies become one, and something remarkable appears. Or perhaps, something remarkable disappears. The spiral arms are gone. The elegant structure has vanished. The graceful patterns that once defined the galaxies no longer exist. In their place stands something entirely different. A giant elliptical galaxy. Smooth, round, massive, ancient-looking. A monument to cosmic transformation. To understand why this happens, imagine a carefully arranged whirlpool. The water rotates in a beautiful pattern. Order exists. Structure exists. Direction exists. Now imagine multiple whirlpools colliding repeatedly. The organized motion becomes scrambled. The pattern disappears. The system settles into something more random, something less elegant, something more chaotic. This is essentially what happens during major galactic mergers. The carefully organized stellar orbits that create spiral structures become disrupted. Stars begin moving in many different directions. The spiral pattern dissolves. Order gives way to randomness. The galaxy becomes elliptical, a giant sphere of ancient starlight. Many of the largest galaxies in the modern universe were probably built this way. Not born large, built large, constructed through countless mergers, layer upon layer of galactic cannibalism. Each collision adding more stars, more mass, more history. The result can be astonishing. Some giant elliptical galaxies contain trillions of stars, several times more than the Milky Way. They dominate the centers of galaxy clusters. Like ancient emperors ruling cosmic kingdoms, massive, powerful, yet strangely quiet, because by the time these giant ellipticals emerge, much of their star-forming fuel is gone, consumed, heated, expelled, or otherwise rendered unusable. The galaxy survives, but its youth does not. The stellar nurseries fade, the blue stars disappear, the future becomes smaller, the past becomes larger, the galaxy enters old age. Many of the dead galaxies observed by astronomers today belong to this category. Gigantic elliptical systems, filled with ancient stars, containing little ongoing star formation, living museums of cosmic history, archives stretching back billions of years. If we could somehow travel into one, the night sky might feel profoundly different. Young blue stars would be rare, bright emission nebulae would be scarce. The energetic signs of stellar birth would largely be absent. Instead, the galaxy would glow with the accumulated light of ancient suns, golden stars, orange stars, red stars, generation after generation of aging stellar populations. A quieter universe, a calmer universe, a universe remembering its past more than creating its future. And perhaps that is why giant elliptical galaxies often feel ghostly, not because they are dark. Many are extraordinarily bright, not because they are empty. Many contain more stars than entire groups of smaller galaxies combined, but because their greatest era of creation lies behind them. Their history outweighs their future. Their memories outweigh their possibilities. They are monuments to what once was, cosmic cities filled with ancient light. And yet, galactic cannibalism is not merely something that happened long ago. It is still happening today, even now, as you listen, as Earth circles the Sunday, as the Milky Way slowly rotates through space. A future collision is already approaching. Far beyond the visible stars, another great galaxy is moving toward us. The Andromeda Galaxy, a colossal spiral containing perhaps 1 trillion stars, larger than our own, massive, ancient, unstoppably approaching. For billions of years, gravity has been drawing our galaxies together, slowly, patiently, inevitably. The distance between them shrinks every moment, not by much. Not enough for human eyes to notice, but enough for the future to already be written. In approximately 4 to 5 billion years, the Milky Way and Andromeda will begin one of the greatest mergers in local cosmic history. Two giant spiral galaxies, each carrying hundreds of billions of stars, each carrying countless planets, each carrying unimaginable histories, meeting at last. The night skies of future worlds will become spectacular. Galactic structures will stretch across entire heavens. Stars will migrate. Gas clouds will collide. New generations of stars will be born. And over immense spans of time, the two galaxies will become one. Astronomers have even given this future galaxy a nickname, Milkomeda, a hybrid descendant, a new cosmic kingdom forged from two ancient parents. And if current models are correct, the resulting galaxy may resemble the giant elliptical galaxies we observe elsewhere. A smoother structure, an older structure, a quieter structure, a future cosmic ghost in the making. The same forces that shaped ancient dead galaxies across the universe may one day shape our own home. The Milky Way is not exempt from cosmic history. It participates in it, just like every other galaxy, born, growing, changing, aging, transforming. The universe makes no exceptions. Yet even galactic cannibalism is only part of the story, because astronomers eventually discovered environments even more hostile than individual mergers, places where thousands of galaxies live together, places where enormous reservoirs of superheated gas fill the darkness, places where galaxies can be stripped of their life-giving material without ever colliding at all. Vast cosmic cities, where entire populations of galaxies slowly drift toward death, under the influence of forces almost impossible to imagine. Chapter 5. Cities of the Dead. Far out in the darkness of the universe, beyond the familiar stars of the Milky Way, beyond the bright spirals that fill astronomy photographs, there exist enormous celestial cities. Ancient cities, silent cities, cities where the great era of creation has already passed, places where generations of stars were born, lived, and died, while almost no new stars arrived to replace them. These are the cities of the dead, the great dead galaxies of the cosmos, and among the most fascinating objects ever discovered. To understand them, imagine visiting Earth thousands of years in the future. Imagine finding vast cities still standing. The roads remain, the buildings remain, the lights still glow, the monuments endure. Yet no children play in the streets, no schools open their doors, no new neighborhoods appear. The city survives, but its future has faded. It has become a place of memory rather than growth, a place defined by what has already happened, rather than what will happen next. Dead galaxies feel remarkably similar. They are not destroyed. They are not ruined. Many remain among the largest and most beautiful structures in existence, yet their age is visible. Their youth has departed. Their stellar nurseries have become quiet. Their brightest days are behind them, and because of this, astronomers treasure them, not despite their age, because of it. For dead galaxies are cosmic archives, libraries written in starlight, ancient records preserving the history of the universe itself. Every dead galaxy tells a story about creation, growth, violence, transformation, and eventually decline. By studying these galaxies, astronomers can reconstruct events that occurred billions of years ago, events long before Earth existed, long before the Sun formed, long before our planet became home to life. Dead galaxies remember, and if we learn how to read them, they reveal the past. Among the most famous examples is the giant elliptical galaxy known as Messier 87, or simply M87. At first glance, M87 may not seem extraordinary. Unlike spiral galaxies, it possesses no graceful arms, no spectacular whirlpool pattern, no bright lanes of gas winding through its structure. Instead, it appears smooth, almost simple, a giant sphere of soft golden light, a diffuse glow suspended in darkness. Yet appearances can be deceptive, because M87 is a giant, a true giant, one of the most massive galaxies in our cosmic neighborhood, containing trillions of stars, perhaps several times the stellar population of the Milky Way. Its diameter stretches across hundreds of thousands of light years. Its gravitational influence extends even farther. M87 sits near the center of the Great Virgo cluster, a vast collection containing thousands of galaxies, like an ancient emperor ruling over a crowded kingdom. And deep within its heart lies one of the most famous objects in modern astronomy, a supermassive black hole of staggering size. The black hole at the center of M87 contains billions of times the mass of our Sun, so massive that human intuition struggles to grasp it. In 2019, it became the first black hole ever directly imaged by humanity. The historic image revealed a glowing ring surrounding a dark shadow, a moment that transformed astronomy. For the first time, human beings looked directly at the edge of a black hole. And that black hole lived inside a dead galaxy, a cosmic ghost hiding one of the universe's greatest monsters. Yet despite its enormous size, M87 forms very few new stars. Its great era of creation largely ended long ago. Most of its stars are ancient. Many were already old when Earth itself was young. The galaxy shines brilliantly, yet much of that light comes from aging stellar populations. M87 is not a city under construction. It is a city preserving its history, a cosmic museum, a monument to billions of years of evolution. And then there is another remarkable example, a galaxy known as NGC 1277. If M87 is a giant city, NGC 1277 is something stranger, a time capsule, a survivor, a relic from another era of the universe. Astronomers sometimes describe galaxies like NGC 1277 as fossil galaxies. The name feels appropriate because fossils preserve ancient life, and NGC 1277 appears to preserve an ancient stage of galactic evolution. This galaxy is unusually compact, remarkably dense, packed with stars, yet despite its extraordinary population, it appears to have stopped forming stars billions upon billions of years ago. Most galaxies continue evolving, changing, growing, merging, transforming. But NGC 1277 seems to have escaped much of that later history. It resembles a galaxy frozen in time, like an insect trapped within amber, a preserved fragment of the young universe. Studying it allows astronomers to glimpse conditions that existed when galaxies were still developing. It is not merely a dead galaxy. It is a historical artifact, a surviving witness from cosmic antiquity. And the more astronomers search, the more dead galaxies they discover. Some are enormous, some are small, some reside within crowded galaxy clusters, others drift through relative isolation. Yet many share common characteristics. They tend to appear redder than living galaxies. This is one of the first clues astronomers notice. Young stars often shine blue, hot, brilliant, energetic, but blue stars live fast and die young. When star formation ceases, those stars gradually disappear. What remains are longer-lived stars, yellow stars, orange stars, red stars. The overall color shifts. The galaxy begins glowing with warmer tones, not because it is physically warmer, but because its population has aged, its light has aged, its story has aged. The galaxy becomes redder, older, more reflective of its past than its future. If living galaxies resemble vibrant spring forests, dead galaxies resemble ancient autumn landscapes, beautiful, yet undeniably mature. and astronomers can often recognize them immediately. Even from billions of light years away, their colors reveal clues. Their structure reveals clues. Their chemical composition reveals clues. Their motions reveal clues. Every measurement adds another piece to the puzzle, another fragment of history, another chapter in the biography of a galaxy. One of the most fascinating discoveries is that many dead galaxies contain surprisingly large numbers of stars packed into relatively small volumes. This suggests they experienced extraordinary periods of growth early in their lives. Perhaps they formed stars at astonishing rates. Perhaps they underwent violent mergers. Perhaps their central black holes became active unusually early. Whatever happened, their histories were dramatic. Many seem to have lived fast and aged quickly, like brilliant civilizations burning intensely before falling silent. Others followed different paths. Some appear to have been slowly starved. Their gas supplies diminished over billions of years, their stellar nurseries gradually fading. A slower journey toward old age, a quieter path into the cosmic graveyard. And this diversity is important because it reveals something profound. There is no single way for a galaxy to die, just as there is no single way for a galaxy to live. The universe rarely follows one script. Instead, it creates countless variations, countless stories, countless destinies. Each dead galaxy represents a unique journey, a unique combination of circumstances, a unique history written across billions of years. This is why astronomers study them so intensely, because dead galaxies help answer some of the biggest questions in cosmology. How did galaxies grow? How quickly did they evolve? What role did black holes play? What role did mergers play? How common is galactic death? How early did it begin? What does the future of galaxies look like? Every dead galaxy contributes evidence. Every observation provides another clue. And perhaps most importantly, dead galaxies allow astronomers to look backward through time, because light itself travels at a finite speed. When we observe distant galaxies, we are seeing the past. A galaxy 1 billion light-years away appears as it existed 1 billion years ago. A galaxy 10 billion light-years away appears as it existed 10 billion years ago. Telescopes become time machines. The farther we look, the deeper into history we travel. And among these distant observations, astronomers have found something surprising. Dead galaxies existed much earlier than expected. Some galaxies seem to have completed their life cycles astonishingly quickly. They formed stars rapidly, grew rapidly, then died, all while the universe itself was still relatively young. These discoveries challenge existing theories. How could galaxies age so quickly? How could they stop forming stars so early? What mechanisms were responsible? The answers remain incomplete. The mystery remains alive. Ironically, dead galaxies continue generating new questions, and perhaps that is their greatest gift. They remind us how much remains unknown. For every mystery solved, another appears. For every answer discovered, new questions emerge. The universe remains larger than our understanding, older than our imagination, and more complex than our expectations. Yet among all these cities of the dead, all these ancient cosmic monuments, one question becomes increasingly difficult to ignore. If galaxies can die, and if so many already have, what does that mean for the future? Not the future of a single galaxy, not even the future of the Milky Way, but the future of the universe itself. Because as astronomers peered farther into the darkness, they began to wonder whether galactic death was merely part of a much larger story, a story involving every galaxy, every star, every source of light, a story in which the entire cosmos may eventually drift towards silence, one galaxy at a time. Chapter 6: Fossils of Lost Galaxies. Long before human beings discovered fossils, long before paleontologists uncovered the bones of ancient creatures, the universe had already been preserving its own history. not in stone, not in sediment, not beneath deserts or mountains, but in starlight, across billions of light years, across billions of years, the cosmos remembers. And some of its most remarkable memories are preserved inside what astronomers call galactic fossils, ancient relics, surviving witnesses, fragments of an earlier universe that somehow endured while everything around them changed. To understand why these objects are so important, imagine discovering a living dinosaur, not a fossil, not a skeleton, an actual dinosaur, alive, breathing, walking, a direct survivor from a vanished world. Scientists would be astonished, because such a creature would provide something fossils cannot: a living connection to the past, a preserved piece of history, a window into an age long gone. Certain galaxies provide exactly this opportunity. They are not merely old. Many galaxies are old. They are ancient structures that somehow escaped much of the transformation experienced by their neighbors. They survived, preserved, almost unchanged, while the universe around them evolved. And because of this, they allow astronomers to study cosmic history directly. They are the fossils of lost galaxies, the survivors of forgotten eras, the preserved ruins of ancient cosmic kingdoms. To appreciate how extraordinary this is, we must remember that galaxies are constantly changing. Throughout cosmic history, galaxies merge, collide, cannibalize one another, accumulate mass, lose gas, form stars, stop forming stars, grow black holes, alter their appearance. A galaxy observed today is often the product of billions of years of modification, layer upon layer of change. Like an ancient city rebuilt countless times, the original structure becomes difficult to recognize. Its earliest form disappears beneath newer additions, newer histories, newer generations. But occasionally, something unusual happens. A galaxy avoids much of this transformation. It remains isolated, undisturbed, protected from the cosmic chaos affecting its neighbors. And as billions of years pass, it preserves clues from an earlier age of the universe. Astronomers sometimes refer to these systems as relic galaxies. The name feels appropriate, because a relic is something carried forward from the past, a surviving fragment, a preserved memory, a message sent across time. One of the reasons relic galaxies fascinate astronomers is that they appear to have formed extraordinarily early. Many seem to have experienced rapid growth shortly after the universe's birth. They accumulated stars, built mass, developed structure. Then, for reasons not yet fully understood, their evolution slowed dramatically. The galaxy became quiet. The galaxy became stable. The galaxy became preserved. While neighboring systems continued changing, the relic remained, waiting, watching, remembering. Imagine standing in a modern city. Glass towers rise overhead. Traffic fills the streets. Technology surrounds you. Now, imagine discovering a perfectly preserved district untouched for 1,000 years. Every building remains intact. Every road remains unchanged. Every detail reflects an earlier age. That district would become priceless to historians. Relic galaxies play a similar role for astronomers. They preserve stages of galactic evolution that might otherwise be lost forever. They show us what galaxies looked like long ago, what conditions existed, what processes shaped the young universe. And because of this, they are among the most valuable objects in astronomy. Some of these relic galaxies appear surprisingly compact. Their stars are crowded together. Their densities are extraordinary. In the modern universe, large galaxies often spread their stars across enormous volumes. But some relic galaxies remain densely packed, almost frozen in their youthful state. This suggests that many giant galaxies we see today may have once looked similar. Over time, mergers expanded them. Interactions reshaped them. New stars altered their appearance. but the relics preserve the original form, the earlier chapter, the first draft of galactic history, a glimpse into how today's giants once began. Yet, individual relic galaxies are only part of the story. Astronomers have also discovered something even more intriguing: entire fossil systems, entire fossil groups, cosmic graveyards preserving evidence of long-forgotten galactic families. To understand fossil groups, imagine a kingdom containing many cities. Over centuries, those cities interact, compete, trade, grow. Some expand, some disappear, some absorb their neighbors. Eventually, one city becomes dominant. So dominant that nearly all rivals vanish. The kingdom remains, but its former diversity is gone. Only one great city survives, surrounded by the remnants of what once existed. This is remarkably similar to what astronomers observe in fossil groups. A fossil group is a collection of galaxies dominated by one enormous central galaxy. Surrounding it, the evidence suggests many other large galaxies once existed. But over billions of years, they merged into the dominant giant. They were consumed, absorbed, erased as independent systems. What remains is a colossal central galaxy, a galactic monarch ruling over a sparse kingdom. The surrounding space often contains extensive reservoirs of hot gas, evidence of the system's ancient history, evidence that numerous interactions occurred long ago, evidence that the giant survivor was built through repeated acts of cosmic cannibalism. When astronomers study fossil groups, they are essentially investigating ancient crime scenes. The victims are gone. The mergers occurred billions of years ago. The original galaxies no longer exist, yet the evidence remains, hidden within starlight, hidden within gas, hidden within gravity itself. The universe leaves clues, and fossil groups preserve them. Some fossil systems appear extraordinarily old. Perhaps among the oldest large structures in existence. They formed early, evolved rapidly, then entered long periods of relative stability. As a result, they provide valuable information about how large-scale cosmic structures emerged. They reveal how galaxy groups evolve, how dominant galaxies grow, how mergers reshape the universe, and perhaps most importantly, they demonstrate that disappearance is not always complete. A galaxy may vanish as an independent object, yet traces remain. Its stars survive, its material survives, its history survives. Nothing is entirely lost. The universe recycles its past. Again and again, this idea appears throughout cosmic history. Stars die, yet their material creates future stars. Galaxies merge, yet their stars continue existing within larger galaxies. Structures disappear, yet their fingerprints remain. The cosmos remembers, even when appearances suggest otherwise. And nowhere is this more evident than when astronomers observe survivors from the early universe. Some of the most extraordinary discoveries of recent decades have come from powerful telescopes peering deep into cosmic history. Looking farther away means looking farther back in time, billions of years into the past, toward an era when the first galaxies were still young. What astronomers found was astonishing. Even in the young universe, some galaxies already appeared surprisingly mature, surprisingly massive, surprisingly old, as though they had evolved faster than expected. Some had already formed enormous numbers of stars. Some had already exhausted much of their fuel. Some appeared to be entering old age while the universe itself was still relatively youthful. These observations challenge existing theories. How could such rapid growth occur? How could some galaxies become so massive so quickly? How could they evolve so far ahead of schedule? The answers remain uncertain, yet the relic galaxies of today may provide clues. Because they preserve evidence of those ancient conditions. They act as laboratories, allowing astronomers to study phenomena that would otherwise exist only in distant cosmic history. In a sense, relic galaxies function like messages in bottles, messages sent billions of years ago, messages that survived cosmic time, messages waiting to be decoded. And perhaps that is what makes them so captivating. Not merely their age, not merely their rarity, but their ability to connect us with lost epochs of the universe. They bridge enormous spans of time. They allow us to look backward, to glimpse conditions that no longer exist, to observe chapters of cosmic history that would otherwise be inaccessible. Every relic galaxy is a survivor. Every fossil group is a monument. Every ancient stellar population is a memory preserved against the erosion of time. And as astronomers continued uncovering these ancient survivors, a deeper realization emerged. Galactic death is not always the end of a story. Sometimes it becomes preservation. Sometimes it becomes memory. Sometimes it becomes a record that future generations can study. The galaxy stops creating, yet it continues teaching. It continues revealing. It continues speaking across billions of years through the language of starlight. And this raises a profound question, perhaps the most personal question in our entire journey. If galaxies age, if galaxies die, if galaxies become fossils, what future awaits our own cosmic home? The Milky Way is alive today. Its spiral arms still glow. Its stellar nurseries still produce new suns. Its future remains open, but nothing in the universe remains unchanged forever. Not stars, not galaxies, not even the great structures that seem eternal. One day, our galaxy too may become a relic, a fossil, a preserved memory of a brighter age. And to understand how that future may unfold, we must turn our attention toward the galaxy we call home, and the long destiny awaiting the Milky Way itself. Chapter 7. The Ghost Light of Ancient Stars. When most people hear the phrase dead galaxy, they imagine darkness, a vast darkness, an empty darkness, a place where the lights have gone out, a celestial ruin drifting silently through space. But reality is stranger, and perhaps more beautiful, because dead galaxies are not dark. Many of them are extraordinarily bright. Some shine with the combined light of hundreds of billions of stars. Some illuminate entire regions of space. Some remain visible across immense cosmic distances. They are dead, yet they glow. Silent, yet luminous. A contradiction written across the universe. And understanding this contradiction reveals one of the most fascinating aspects of galactic death. Because a dead galaxy does not stop shining when star formation ends. In many cases, it continues shining for billions upon billions of years, long after its stellar nurseries fall silent, long after its final generations of stars are born, long after its youth has disappeared. The reason is simple. Galaxies do not shine because they create stars. They shine because they contain stars. And stars can live for astonishing lengths of time. To understand why dead galaxies remain luminous, we must leave the scale of galaxies behind. For a moment, we must focus on the stars themselves. Every star has a life story, a beginning, a middle age, an old age, and eventually, an ending. The details depend largely upon mass. Mass determines destiny. Mass determines lifespan. Mass determines how a star will die. Some stars live fast. Some stars live slowly. The most massive stars in the universe are cosmic fireworks. Brilliant, hot, blue. They burn through their fuel with incredible speed. A star dozens of times more massive than the Sun may survive only a few million years. A brief instant by cosmic standards. These stars shine with extraordinary intensity. Yet they pay a price. The brighter the flame, the faster the fuel disappears. Massive stars live spectacular lives, and spectacularly short ones. By contrast, smaller stars are patient, careful, efficient. They burn their fuel slowly, methodically. A red dwarf star can survive for trillions of years, far longer than the current age of the universe. In fact, the universe is not yet old enough for even a single red dwarf to have reached the end of its life naturally. Every red dwarf ever formed still exists, still shining, still waiting, still enduring. The cosmos contains stars with lifespans so immense that no human civilization can truly comprehend them. And this is why dead galaxies continue glowing, even after star formation ends. The stars already present remain alive. Millions, billions, hundreds of billions of suns, continuing their journeys through time. The galaxy stops creating, but it does not stop existing. The stellar population continues aging together, like a vast civilization entering old age, generation after generation moving forward through time. And as this happens, the appearance of the galaxy changes. The young stars disappear first, the hot blue stars, the brilliant white stars, the short-lived giants. They burn brightly, then die. Without new star formation, there are no replacements. Gradually, the youthful population vanishes. The galaxy begins losing its blue light. The color shifts, subtly at first, then more noticeably. The galaxy becomes warmer, redder, older. This is one reason astronomers often describe dead galaxies as red galaxies. The color itself becomes evidence of age, evidence of declining star formation, evidence that the stellar population has matured. But the story goes deeper than color, because as stars age, they themselves transform. And among the most beautiful stages of stellar evolution is the red giant phase. One day, billions of years from now, our own sun will become a red giant. The hydrogen fuel in its core will become depleted. The internal balance sustaining the star will change. The core will contract. The outer layers will expand. The sun will grow enormously larger. Its appearance will transform. Its color will shift. Its light will change. The familiar yellow star of today will become something entirely different. A giant ember glowing within the darkness. A red giant. Throughout the universe, countless stars experience this transformation, especially in old stellar populations. Dead galaxies often contain enormous numbers of red giants. Their presence contributes significantly to the galaxy's warm coloration, to its soft golden glow, to the feeling of ancientness conveyed by its light. If a young galaxy resembles a bustling city filled with energetic youth, a dead galaxy resembles a grand gathering of elders. Not weaker, not lesser, simply older, filled with stars carrying immense histories, stars that have witnessed billions of years of cosmic change. Some red giants become truly enormous. If placed where the sun currently sits, their outer layers could engulf the orbits of inner planets, Mercury, Venus, perhaps even Earth. The scale becomes difficult to imagine, stars expanding to hundreds of times their original size. A final act of grandeur before the end. Yet even red giants do not last forever. Eventually, for stars similar to the Sunday, another transformation occurs. The outer layers drift away into space, expanding slowly, creating glowing shells of gas. Beautiful structures known as planetary nebulae. Despite the name, they have nothing to do with planets. The term emerged centuries ago when early telescopes made these objects appear vaguely planet-like. In reality, they are stellar farewell messages. Final gifts from dying stars. Expanding bubbles of illuminated gas, floating through the darkness. Then, after the outer layers disperse, the core remains. Small, dense, extraordinarily hot. A white dwarf. White dwarfs are among the strangest objects in existence. Imagine compressing the mass of a star into a sphere roughly the size of Earth. Matter becomes unimaginably dense. A single teaspoon of white dwarf material would weigh tons. Yet despite their density, white dwarfs no longer generate energy through fusion. Their great stellar engines have stopped. They shine because they are hot. not because they are producing new energy. They are cosmic embers, slowly cooling, slowly fading, over immense periods of time. Dead galaxies contain countless white dwarfs, entire populations of them, silent stellar remnants scattered throughout the galaxy, invisible individually across great distances, yet collectively contributing to its history, its structure, its memory. Every white dwarf represents a star that completed its journey. Every white dwarf is evidence of a life already lived, and as billions of years pass, their numbers continue growing. The galaxy accumulates stellar ghosts, not supernatural ghosts, but astrophysical ones. Remnants, survivors, echoes of stars that once shone differently. The remarkable thing is that even these remnants continue radiating light. For extraordinary lengths of time, white dwarfs cool very slowly indeed. A white dwarf formed today may continue glowing for trillions of years, long after civilizations vanish, long after planets change, long after galaxies themselves evolve. Patience seems woven into the fabric of the universe. Everything fades, but often far more slowly than we expect. And this slow fading creates one of the most haunting aspects of dead galaxies. They become illuminated by history. Their light increasingly originates from ancient stars, ancient stellar populations, ancient survivors. The galaxy becomes a collection of memories, a luminous archive, a museum built from aging suns. Imagine standing somewhere within such a galaxy. The night sky would be different, not empty, not dark, but different. Few brilliant blue stars would dominate the heavens. Few stellar nurseries would glow. The dramatic signs of cosmic youth would be largely absent. Instead, the sky might appear calmer, softer, more subdued, a landscape of mature starlight. An ancient population quietly continuing its journey through time. There is something almost poetic about this. Galaxies spend billions of years creating stars, building populations, expanding their stellar communities. Then, when creation ends, those stars continue illuminating the darkness. The galaxy lives on through them. Its past becomes its light. Its history becomes visible. Its memories become luminous. And perhaps this is why dead galaxies feel so haunting. Not because they are empty, not because they are dark, but because they shine with the accumulated light of the past. Every photon carries history. Every glow represents stars born long ago. Every warm color speaks of ancient populations aging together. Dead galaxies are not places where light has vanished. They are places where old light dominates. Places where youth has faded, but memory remains. And in some cases, that memory is extraordinarily ancient. Many dead galaxies contain stars that formed more than 10 billion years ago. Stars born when the universe was still young. Stars that existed before Earth, before the Sunday, before our solar system. Stars older than almost everything familiar to us. Their light has traveled across cosmic ages, persisting, enduring, surviving, like messages sent from forgotten epochs. The longer astronomers study these ancient stellar populations, the more they realize something profound. Dead galaxies are not merely endings. They are records. Records of how the universe once looked, how stars once formed, how galaxies once evolved, how cosmic history unfolded. And because these records survive, they allow us to reconstruct the past, to read chapters written billions of years ago, to understand events that no human observer ever witnessed. The dead continue teaching the living. The past continues illuminating the present. And yet, even these ancient stars will not shine forever. The red giants will fade. The white dwarfs will cool. The remaining stellar populations will continue aging. The ghost light itself will slowly weaken. Trillions of years from now, far beyond the age of galaxies as we know them, the universe will enter an era even stranger, an era when most stars are gone, when creation has largely ceased, when darkness becomes increasingly dominant, an era sometimes called the degenerate age, the distant future of the cosmos, the ultimate fate awaiting not merely dead galaxies, but perhaps every galaxy in existence. And to understand the full meaning of cosmic death, we must journey farther than ever before, far beyond the present universe, far beyond living galaxies, far beyond the age of stars themselves, into the unimaginable future, where the last lights of the cosmos begin to fade. Chapter 8. The Age of Black Holes. So far, our journey has taken us through the graveyards of galaxies. We have watched stellar nurseries fall silent. We have witnessed galaxies grow old. We have followed cosmic collisions, studied ancient relics, explored the ghostly remains of systems that no longer exist. Yet everything we have discussed belongs to a universe that is still relatively young, a universe filled with stars, filled with galaxies, filled with light, a universe that still possesses tremendous energy, tremendous activity, tremendous possibility. The cosmos today may seem ancient to us. After all, it is nearly 14 billion years old. 14 billion years, a number so large that the human mind struggles to visualize it. Entire civilizations rise and fall in mere thousands of years. Mountains form and erode across millions. Species evolve across millions. Planets change across billions. And yet, compared to the future awaiting the universe, the present moment is astonishingly young. The cosmos is still in its youth, still early in its story, still near the beginning. If the entire future history of the universe were compressed into a single year, everything humanity has ever known would occur within the first tiny fraction of a second. The vast majority of cosmic history has not happened yet. It remains ahead, waiting, unwritten, and as we travel farther into that unimaginable future, we discover something remarkable. The stars do not last forever. The galaxies do not last forever. Even the great cosmic structures that seem eternal eventually fade. One by one, the familiar landmarks of the universe disappear, and in their place, something else begins to dominate. Something dark, something ancient, something almost immortal. Black holes. To understand the age of black holes, we must first understand the fate of the stars. Stars are the engines of the cosmos, the primary source of visible light, the creators of heavy elements, the architects of planets, the builders of possibility. For trillions upon trillions of years, stars continue shining. New stars form. Old stars die. The cycle persists. But eventually, the raw materials required for star formation become increasingly scarce. Galaxies exhaust their gas. Stellar nurseries vanish. The birth rate declines. The great age of stellar creation slowly comes to an end. Not suddenly, not catastrophically, gradually, patiently, like a fire consuming its final fuel. Across the universe, fewer stars are born, then fewer still, then almost none. The stellar era begins ending. Astronomers sometimes call this period the stelliferous era, the age of stars. It includes the present universe. It includes the galaxies we know. It includes the Milky Way. It includes Earth. It includes us. Yet it is temporary. Eventually, billions become trillions. Trillions become quadrillions. Time stretches beyond imagination. The final generations of stars continue aging. Many die, others endure. Red dwarfs become increasingly important. These tiny stars are astonishingly efficient. They burn fuel so slowly that they can survive for trillions of years, far longer than stars like the Sun, for unimaginable spans of time. Red dwarfs dominate the universe, tiny embers scattered across the darkness, the last representatives of the stellar age, the final guardians of starlight. Yet even they do not last forever. Eventually, even the longest-lived stars exhaust their fuel. The universe grows darker, The great age of stars concludes, and a new era begins, an era unlike anything humanity has ever experienced. The degenerate era, a universe populated primarily by remnants, white dwarfs, neutron stars, black holes, the corpses of stars, the leftovers of creation, the ashes of cosmic history. Galaxies still exist, at least for a time, but they look different, much different. The brilliant spiral arms are gone, the stellar nurseries are gone, the energetic blue stars are gone. The universe becomes quieter, older, more contemplative, a vast landscape of remnants drifting through darkness. Imagine standing in such a universe. If standing were even possible, the familiar night sky would be unrecognizable. No glowing Milky Way, no brilliant constellations, no bright stellar populations, only scattered remnants, ancient survivors, the lingering echoes of an earlier age. And over even greater spans of time, something extraordinary happens. Galaxies themselves begin dissolving, not physically at first, dynamically. Gravitational interactions slowly eject stars. Objects pass near one another. Energy is exchanged. Over countless encounters, many stars gain enough velocity to escape. The galaxy gradually loses members, like grains of sand slipping from a vast cosmic hourglass. The process is incredibly slow. Yet, given enough time, even galaxies unravel. Stars drift into intergalactic space. White dwarfs wander alone. Neutron stars wander alone. Black holes wander alone. The great structures of the cosmos begin coming apart. Order gives way to isolation. The universe becomes increasingly empty, increasingly dark, increasingly silent. And amid this growing darkness, black holes remain. Black holes endure. They survive the death of stars. They survive the death of galaxies. They survive the collapse of familiar cosmic architecture. Indeed, the farther we travel into the future, the more dominant they become. Entire galaxies may eventually consist primarily of black holes and stellar remnants, the descendants of countless generations of stars, the accumulated remains of cosmic history. This is why astronomers sometimes speak of a future age of black holes, an era in which black holes become the most important large objects remaining in the universe, the great survivors, the final monarchs of cosmic evolution. At first glance, this seems strange. Black holes are often imagined as destroyers, as endings, as cosmic predators, yet in the distant future, they become preservers, the last major structures still existing, the last concentrated reservoirs of mass, the last echoes of a universe once filled with light. For incomprehensible lengths of time, black holes dominate. Millions of years pass, then billions, then trillions, then numbers so large that language begins failing. 1,000,000 trillion years, 1,000,000,000 trillion years, vast oceans of time. The universe continues expanding. Galaxies become isolated beyond imagination. Distances grow, darkness deepens, and still the black holes remain, patient, silent, enduring. It would be tempting to think they last forever. For many years, some scientists did. Black holes seemed eternal, the ultimate survivors, objects from which nothing could escape, perfect cosmic prisons. But then, in the 20th century, a remarkable idea emerged, an idea proposed by the brilliant physicist Stephen Hawking, an idea so surprising that it changed our understanding of black holes forever. According to Hawking's calculations, black holes are not completely black. They are not entirely silent. They are not entirely eternal. Instead, they slowly emit energy, an extraordinarily tiny amount, a process now known as Hawking radiation. The concept is subtle, deeply rooted in quantum physics. Yet its implications are profound, because if black holes emit energy, they lose mass, and if they lose mass, They eventually disappear. The process is unimaginably slow. A stellar mass black hole may require far longer than the current age of the universe to evaporate. A supermassive black hole requires vastly longer still. Numbers become almost absurd. A black hole containing billions of solar masses may survive for periods measured in years with dozens of digits. Time scales so immense that ordinary intuition collapses entirely. Yet even the greatest black holes are not immune. Given enough time, they shrink, slowly, patiently, imperceptibly. The giants of the cosmos begin fading. Imagine the last supermassive black hole scattered across an almost empty universe. The descendants of the monsters that once lived inside galaxies, the descendants of the giants that helped shape cosmic history for epochs beyond imagination. They remain, the final monuments of a vanished age. Then, one by one, they evaporate, not through violence, not through collision, but through the slow leakage of energy into the darkness, the ultimate act of fading, the final surrender. And as each black hole disappears, something extraordinary happens. A tiny burst of radiation emerges, the last whisper of an object that may have survived for unimaginable durations, the final breath of a cosmic giant. Then silence, complete silence. By this stage, the universe has changed beyond recognition. The stars are gone, the galaxies are gone, the stellar nurseries are gone, the great clusters are gone. The familiar structures that once defined the cosmos have vanished. Only scattered particles remain. Photons, electrons, positrons. Tiny fragments drifting through expanding space. The universe approaches simplicity once more. A strange symmetry. Near the beginning, the cosmos was simple. Near the end, it becomes simple again. Not because it returns to its original state, but because complexity gradually fades. The grand architecture built over trillions upon trillions of years dissolves. The great cosmic cities disappear. The galaxies disappear. The stars disappear. Even the black holes disappear. Everything familiar becomes memory. Everything recognizable becomes history. And yet, there is something strangely peaceful about this vision. The universe does not end in a great explosion. Not necessarily. It does not collapse dramatically. It does not rage against its fate. Instead, it simply ages. Ages on scales beyond imagination, moving slowly toward darkness, moving slowly towards silence, moving slowly towards stillness. The same pattern we observed in galaxies, the same pattern we observed in stars. Creation, growth, maturity, decline, fading, the life cycle repeated on the largest possible scale, the life cycle of the cosmos itself. And perhaps that is the final lesson hidden within the graveyards of galaxies. The dead galaxies we observe today are not anomalies. They are previews, glimpses of a future awaiting larger structures. Galaxies age, stars age, black holes eventually fade. The universe itself evolves. Everything changes. Everything transforms. Everything leaves traces. And as we drift through the darkness of cosmic time, past ancient galaxies, past stellar ghosts, past vanished civilizations of stars, we find ourselves surrounded by something extraordinary. Not emptiness, not meaninglessness, but history, layer upon layer of history, written across the universe, preserved in light, preserved in gravity, preserved in the silent ghosts of galaxies that once blazed brilliantly across the darkness. And as the cosmos continues its endless journey through time, another question begins to emerge from the silence. A question not about the death of galaxies, but about what their existence reveals about our own place in this vast and ancient universe. Chapter 9. After the last galaxy dies, there is a moment hidden somewhere in the future, a moment so distant that every human language will have vanished long before it arrives. Every nation, every civilization, every mountain, every ocean, every planet, every star familiar to us today, gone, not because of catastrophe, not because of violence, but because time itself continues moving forward, patiently, relentlessly, without pause, without mercy, without intention. And somewhere within that unimaginable future, there comes a day when the final galaxy dies. Not the Milky Way, not Andromeda, not even Milkomeda, the final galaxy, the last great city of stars remaining anywhere in the observable universe, the last island of organized light, the last monument to an age when galaxies filled the cosmos. And when that final galaxy fades, an entire chapter of cosmic history closes forever. For nearly 14 billion years, the universe has been a place of structure, a place of complexity, a place of creation. Galaxies formed, stars ignited, planets emerged, elements combined, life became possible. The universe built things, it assembled wonders. It transformed simplicity into complexity, yet hidden beneath all this creation, another process has always been operating, a quieter process, a deeper process, one that governs the ultimate destiny of everything, entropy, the tendency toward disorder, the tendency toward equilibrium, the tendency toward balance. It is one of the most fundamental principles in all of physics. And although stars can temporarily create order, although galaxies can temporarily create beauty, the long-term direction remains unchanged. The universe slowly moves toward greater uniformity, toward greater simplicity, toward a state where usable energy becomes increasingly rare. This ultimate destination is often called the heat death of the universe. The name sounds dramatic, yet it can be misleading. Heat death does not mean the universe becomes hot. Quite the opposite. It means temperature differences disappear, energy gradients disappear, the conditions required for complex activity disappear. Everything approaches equilibrium, everything approaches sameness, everything approaches stillness. To understand why this matters, imagine a river. Water flows because differences exist. Higher elevations, lower elevations, potential energy, movement. Now imagine the river eventually becoming perfectly flat. No higher points, no lower points, no gradients, no flow. The motion ceases. The system reaches equilibrium. Something similar happens to the universe. Stars shine because energy differences exist. Life exists because energy differences exist. Galaxies evolve because energy differences exist. When those differences vanish, activity becomes increasingly difficult. The cosmos slowly quiets. By the time the last galaxies disappear, the universe has already changed beyond recognition. The great clusters are gone. The giant elliptical galaxies are gone. The spiral galaxies are gone. The stellar nurseries are gone. Even most stars are gone. What remains are remnants. White dwarfs, neutron stars, black holes, scattered particles, ancient survivors drifting through enormous darkness. Distances continue expanding. Galaxies that once occupied neighboring regions become separated by unimaginable voids. The expansion of space never stops. The darkness grows. The isolation grows. The loneliness grows. Imagine standing within such a universe. If standing could still have meaning, the night sky would no longer exist as we understand it. There would be no Milky Way, no constellations, no visible galaxies, no glowing band of stars stretching across the heavens, only darkness. Almost complete darkness. The great cosmic cities would have vanished. The universe would become a vast ocean without islands, an infinite desert without landmarks, a place where history itself becomes difficult to detect. And yet, even after the death of galaxies, the story continues. Because remnants endure, white dwarfs continue cooling. For trillions upon trillions of years, Their faint heat slowly radiates into space, each one becoming dimmer, redder, colder. Eventually, after unimaginable spans of time, they become black dwarfs, objects that are purely theoretical today. The universe is not old enough for any black dwarfs to exist yet. Not a single one. Every white dwarf ever created is still cooling, still fading, still making its journey toward darkness. But in the distant future, black dwarfs become common, the silent corpses of ancient stars, invisible monuments to a vanished stellar age. Neutron stars endure as well, compact remnants left behind by supernova explosions, entire stars compressed into spheres only kilometers across, incredibly dense, incredibly ancient. For immense periods of time, they survive, preserving evidence of long-dead stellar populations. Black holes survive longer still, far longer. They become the final great structures of the cosmos, the last giants, the last monuments, the final rulers of a universe growing increasingly empty. Entire epochs become defined by their existence. The age of black holes, a period so long that all previous cosmic history begins to seem brief by comparison. And yet, even black holes eventually fade, through Hawking radiation, through the slow leakage of energy into space. The process is unimaginably gradual. A supermassive black hole may survive for periods so vast that ordinary numbers become meaningless. Millions of digits may be required simply to write the duration. Yet eventually, the end arrives. Even for them, the final black holes evaporate. One by one, across the darkness, the last great engines of gravity disappear. The last great repositories of history vanish. The final cosmic monuments crumble. And after that, the universe enters a phase almost impossible to visualize. Because nearly everything familiar is gone. No stars, no galaxies, no nebulae, no black holes, no planetary systems, no stellar clusters, no spiral arms, no giant ellipticals, no visible architecture. The cosmos becomes astonishingly simple. Particles, radiation, expansion, silence. This is the universe after the last galaxy dies. A universe where history survives only in fragments. The descendants of all cosmic structures reduced to scattered remnants, like the final dust of a civilization whose cities have long since vanished. And yet, even in this darkness, the past leaves traces, because the universe remembers. The same lesson we encountered again and again throughout our journey. Destroyed galaxies leave stellar streams. Ancient mergers leave halos. Dead galaxies preserve stellar populations. Black holes preserve mass. Nothing disappears completely without leaving evidence behind. History lingers, sometimes for billions of years, sometimes for trillions, sometimes for periods so vast that language cannot adequately describe them. The final universe becomes a museum of remnants. A museum with no visitors. A museum with no lights. A museum whose exhibits slowly fade. Yet a museum nonetheless. Every particle carries history. Every photon carries history. Every surviving fragment originates from events that occurred billions or trillions of years earlier. The cosmos becomes an archive written in fading traces, and perhaps that is the strangest aspect of the heat-death scenario. It is not an explosion. It is not a catastrophe. It is not a dramatic ending. The universe does not rage against its fate. It does not collapse in fury. It does not burn in one final blaze of glory. Instead, it simply grows quieter. The lights go out one by one. The structures disappear one by one. The complexity diminishes one step at a time. The ending resembles an evening, a very long evening, an evening lasting longer than imagination itself. The stars disappear like distant lamps. The galaxies fade like cities beyond the horizon. The black holes become the final embers. Then they too vanish, Darkness spreads, silence deepens, the cosmos enters its longest night. Yet even here, at what appears to be the end of everything, uncertainty remains, because physics itself may not have revealed all its secrets. Some theories suggest new phenomena could emerge. Some propose quantum events occurring across unimaginable timescales. Others suggest that entirely new universes might arise from processes we do not yet understand. Perhaps the heat death truly represents the final chapter, or perhaps it is merely the final chapter we currently know how to read. The universe has surprised humanity before, again and again. Every generation believed it understood the cosmos. Then new discoveries arrived, new mysteries appeared, new questions emerged, and so honesty requires acknowledging something important. No one knows with absolute certainty what lies beyond the deepest future. The ultimate fate of reality itself remains one of the greatest unanswered questions in science. Yet regardless of the details, one truth remains. Everything we have explored throughout this journey forms part of a single story, the story of cosmic evolution. Galaxies are born, galaxies grow, galaxies merge, galaxies age, galaxies die. The universe itself evolves through similar stages: creation, growth, transformation, decline, silence. The dead galaxies we visited were never isolated curiosities. They were chapters within a much larger narrative, a narrative stretching from the first moments after the Big Bang to the final fading of the last remnants of cosmic history. And as we drift now through the deepest darkness imaginable, past the ghosts of galaxies, past the fossils of ancient stars, past the ruins of cosmic empires, we find ourselves surrounded by something unexpected. Not despair, not emptiness, but perspective, because every galaxy that ever lived, every star that ever shone, every planet that ever formed, every atom inside every living creature belongs to the same story. A story billions of years old, a story still unfolding, a story written across the entire universe. And tonight, for a brief moment, you have traveled through its graveyards. You have wandered among cosmic ghosts. You have witnessed the rise and fall of galaxies. You have followed starlight from birth to extinction. You have crossed epochs so vast that civilizations vanish like sparks. And now, as the final galaxies fade into the darkness, as the last echoes of creation drift silently through space, as the universe itself settles into stillness, the darkness no longer feels empty, because it is filled with memory, filled with history, filled with the lingering echoes of everything that ever was. And somewhere within that endless cosmic night, the ghosts of galaxies continue their silent journey, through time, through darkness, through eternity.